Hello everyone, my name is Daniel Rodriguez Criado and welcome to my presentation of our work for creating a toolkit to generate social navigation datasets. My colleagues are Risha Bahel, Aditya Kapoor, Pilar Bachiller, Ronit Jorbekar and Luis Manso. I want to start with a brief introduction to explain why social navigation datasets are useful and necessary, and also to provide a bit of context. Mobile robots and mobile robots are gradually becoming part of our society, and they are expected to be incorporated in our daily life in the future. For this reason, we should devise navigation models that are human aware, so this robot will have a better acceptance. The term of human awareness implies to consider several aspects. One of them is the human emotions. For example, imagine a scenario where two people are having an argument. In that case, probably the robot should avoid to approach the guest to offer a drink or any kind of service. Another thing that robots should consider is to interpret human intentions and goals. This plays an important role in navigation because that way robot can predict human paths and avoid collisions or discomfort to them for getting too close. Another key parameter is the behavior and social conventions in the environment. A robot that behaves like a human tends to be more predictable and easier to interpret. Finally, I want to mention to point out that most of the current algorithms in social navigation use machine learning approaches. Before social navigation models become more trendy, they were all manually programmed. So that this approach has some drawbacks. For example, in social navigation, there are a lot of variables to consider, which requires a lot of time to program manually. And some of them that might be important for the model can be disregarded even from experts. So for training machine learning models using supervised learning in social navigation, we need to generate a considerable amount of data, and for this reason, our contribution with this paper is a toolkit that generates social navigation datasets, and that can be used for training a machine learning model. To prove that, we additionally show a use case where we train a graph neural network for making a robot uh, use or do path planning following the social rules. So now I will move on to some literature review about social navigation datasets. In a general classification, they can be divided in two types, simulated or real. Recording videos for dataset with real environment is relatively easy and inexpensive task. However, the videos need to be annotated, and even if there is some algorithms for detecting the people in the video and do this task automatically, this have to be supervised by a human in the end. So on the other hand, we have the simulated dataset that has the advantage of generating uh, annotated data from the ground truth that is provided by the simulator. They present a main drawback, that is the simulator only approximated the real data, and this can introduce some bias in the dataset. Our tool provides simulated and dynamic scenarios where people can move freely, and being dynamic provide the time parameter, and the models can take it into consideration. So the main gap in the literature review that we found is that most of the current datasets provide information about how pedestrian moves, but not how people would like robots to move. And these two things can be different sometimes. For example, if the robot is heavy or has a or can be potentially harmful for humans, it could be interesting to make it especially careful regarding social distances. I also want to mention that there is a private dataset considering this aspect of how people would like robots to move, but it only provides static scenarios. So we introduced that improvement of dynamics scenarios in our tool. So now, in this image, we can see the structure of our toolkit. It is called Social Navigation Toolkit for Data Acquisition, or Sonata. As you can see, it is a modular tool composed of 3 different software components that can be used as scaffolding to implement different dataset generation tools. The module is built on top of PyRep that is used to communicate with Coppelia Sim Simulator. So it provides a high-level API to interact and control the simulation and also have the function of recording the generated data. The simulator component acts as an interface with the simulator, providing information about the people, walls, objects, and goals in the simulated scenario, and also can send commands to the simulator, like the one for moving the robot. There is another component that is the event publisher. It receives events from a joystick or a mouse and publishes them. So these two components are common to any Sonata implementation. They don't vary from implementation to implementation. And the only problem-specific component is the controller that is subscribed to events from the event publisher and the simulator. With the information from that events, the controller is in charge of gathering data and controlling the simulation, like moving the robot and the humans in the scenario. The the user of the toolkit can modify the controller code uh, to custom its functionality for a specific problem. So the control loop of the default controller periodically associate the state of a scene with the label specified by the user and store this label data in a JSON file. So in this image, you can see the different topics that the controller is subscribed to. The table D comes from the event publisher and the rest from the simulator. As you can see, it is geometric information about the entities in the room and semantic information of the interactions, as you can see in the table F. So in this slide, you can see an example of the GUI of the application. It shows a third-person view of the robot, providing a general view of the scene. And it also have a button to set up some configuration, another one to regenerate the scene, and another one to quit the simulation. The text input is to provide some ID of the contributor for labeling purposes. And we will see all of this in more detail in an example video later. So now I will talk about the use case to test the usefulness of the dataset. The aim is to train a relational graph neural network with data generated using Sonata. For that, the authors of this paper as contributors have used the tool for recording social compilant path to a goal in a scenario of a room with a variable number of people and objects. The information of each frame is stored, and also the command from the contributor that will be the label for training the model. And we generate in total 6,184 samples. And with this data, we have to create the graphs that will be input to the GNN. And this graph just encode the information of each entity in the room as nodes. So one node for each human, object, and wall, and an additional node for the goal, and also one for the robot that acts as a global node because it's connected to the rest of the nodes in the graph. Also, if two humans or a human and an object are interacting, their respective nodes are connected by an edge. This encodes the information of the interactions. So the final graph is created by connecting three graphs from three consecutive frames, and this is because that way the temporal evolution of the entities are considered. And at this point, I also want to highlight that this dataset focuses on structured data. So this kind of models, the graph neural networks, can take a good advantage of it. So now uh, I will show you a video of how we gather the data using Sonata tool. First, it asks you for the name of the contributor. Before starting, you can use the configuration button to set some values for number of humans and objects with a minimum and a maximum. And as you can see, the screen has a green color before starting, and when you start moving the robot, it will disappear, as you can see. So we try to lead the robot to the goal, respecting some social norms like keeping distance from humans and avoiding uh, to go through iterations. These iterations are shown as blue lines on the floor. The goal is shown as a green circle on the floor and a red cone. And when you finish it, as you can see, you can save the data or discard it. Once the model is trained, we will see the results in two videos. The first one is social complement, but in some cases, the robot get too close to humans or even collide with them because some of the scenarios are too complex, and that might be solved with more data. So, for example, this is the scenario where the model can bring the robot to the goal safely and avoiding contact with people and also respecting the distance. So as you can see, it go to the goal, but keeping interpersonal distance with humans. And at the end, it reached the goal. And in the video, as you can see, it gets too close with humans because the environment is too crowded. Before finishing, I want to point out some limitations that will be tackled in future works. First, we don't provide a HUD-like display to provide information on top of the image. For example, when the goal is out of view in the scene, we could use that to tell the user where to go to find the goal. Also, sometimes the humans go through walls that are supposed to be solid. This is a bug that we have to solve. And in this dataset, we don't consider the orientation of the head. It is interesting to consider that in future versions because gaze is an important cue for social navigation. So that's all. Thank you very much for your attention.